Forward, reversing, laser pointer. Did you do that when you were a research assistant?
I was right. I earned. That's how I earned my tuition. Was I was actually a full-time swim coach and happened to be a PhD student at the same time. Yeah, while I was a PhD student.
Okay.
All right. Well, I think we're ready to get started here. I think there's enough sound coming out here to work. I'd like to introduce Professor Brad Lehman, who's a faculty member at Northeastern University in Boston. He avoided all the traffic today from the Boston Marathon and decided to come here instead. So we're happy to have him, and it's a nice day here too. So I wanted to introduce him because he's also an alum. He got his BS at Georgia Tech, his MS here at Illinois, and doctorate at Georgia Tech. He worked his way through his doctorate by being the swim coach at Georgia Tech, which I thought was always really interesting. And although he's a professor at Northeastern, a lot of his day job right now is actually as editor-in-chief of the IEEE Transactions of Power Electronics. So I hope he doesn't have too many more stories about that. But I wanted him to give us a talk about some of the key things he's doing, specifically in solid-state lighting and the control and operation of those kinds of devices. So please welcome Professor Lehman.
Thank you. So I really didn't know what the expertise would be here, and it's flexible, so as you have questions about different subjects that I'm going over, anything about LED lighting, please feel free to interrupt me, and I have so many slides I can just go over and skip a bunch of them. I've recently sold a company to Akrish, which is the biggest solid-state lighting in Korea, and so now I'm able to speak very freely about the industry of LED lighting. Okay. But first of all, let me just say that I'm also the chair of IEEE standards group, so anything that I say today would not reflect that standards group, but would only be my opinion. It's the usual disclaimer. Okay, but this is the outline. We'll go over introduction to LED lighting, because probably some of you are mildly familiar with it. Then we'll talk about something which is flicker in LED lighting. It's kind of fun in some ways because you really don't have to have expertise to really understand the issues of flicker and what's going on. But something is happening that maybe none of you are really aware of, and it's something that power electronic engineers need to know about. And that's the idea of flicker in lighting, because different LED drivers actually cause different amount of flicker, and they can have different health effects. So often what we do in the field, we don't think about how it's going to affect the well-being of society. We might think about power efficiency and then greenhouse gases, but how about what you do might affect how people physically feel? Will it give them a headache or will it not? Could it even, to the extreme, cause seizures? And it is possible that that could happen, a poorly designed driver. But let's just do some background on lighting. What is the big deal about LED lighting? I think what we can say is that we're engineers. We can understand something called cost of ownership on a life cycle. Now, to date, we can see that LED lightings, like you can get at Lowe's or Home Depot, which are typical lumen output of a 60-watt bulb, an incandescent, they're very competitive in lumens per watt to a CFL. But if you look at the 25,000 hour life cycle cost, what they're claiming is that it's a little bit cheaper even now. Now, the initial investment would be a little bit higher. It's about $10 per lamp, maybe $5 per lamp here. Now, notice what we've got here is I've got $5 per lamp for a CFL, and you think you might be able to get them cheaper. But anybody who's ever put in a CFL from Home Depot or something knows that those don't really last the amount of time that they claim they do. But my experience has been, from me marking how long they last, that if I paid $5 per lamp, I can get them to last about 12,000 hours. That's what I think, although still they're going on. But the point here is that, they're very efficient and they have a longer lifetime. One thing about LEDs is the LEDs themselves do not fail, but they gracefully degrade. So you have to say, what do you call that it fails? So let's say you might say 70% of the original output or 50%, depending on how you're defining it. The 25,000 hour is a 50%. But people like LED lighting. You can do a variety of different things. There's the Hard Rock Hotel in Las Vegas, the different colors, that's the Louvre. White LEDs, color LEDs, fancy restaurants, accent lighting, bars. I have a friend, he was one of the co-founders of a company called Color Kinetics, and it was bought by Philips for $1 billion. The story about that is that, I invested in it, even though they were a competitor, because he was a friend of mine. And so I made a lot more money in his company than I did in mine for the entrepreneurs in there. And he has stories about how he and his company did this bridge called the Hudson River Bridge, and they put, I don't have a picture of it, of colored lights. And then there was a bar where you, underneath the Hudson River Bridge, and a woman would pass by, he'd say, "What's your favorite color?" And she'd say pink. He'd program pink, and all of a sudden the bridge would turn pink. And he could just play those games. And if you look at my kitchen, I have that same thing, disco lights, $3,000 disco lights. So they were more of a toy at that time, really, let's be honest. Now, though, what we can say is, besides the beauty, that they are beginning to see their solid state lighting. So the price is coming down by Moore's law. And to a point that we can project, it's following the trajectory, that it won't be long where you really will go in and for a few dollars, you're going to get maybe end of 2015, a few dollars, you'll get an LED bulb that would be, comparable to the cost of a CFL, but should last longer. Okay? So I think the bottom line is that the quality of light is very good. Now, the lighting in here is not very good, but you can see, here I am, I'm lit by a CFL. It's got a little bit bluish tinge, okay? And some people don't like CFLs because of that. Here's an incandescent. The lighting's not great in here, but it's a little bit oranger, so the incandescent bulbs are here. And then I have here with an LED, and once again, the lighting's not good, so you might not be able to see the quality, but there I am. So I apologize for the bad graphics. But why LEDs? LEDs last about 50,000 hours, depending on how you define them. Now, that's the LED bulb themselves. We have electrolytic capacitors that you have to deal with, and electrolytic capacitors do not necessarily have that lifetime, right? So that's leading to different types of topologies, where in fact what since I'm part of this community that's done these topologies, I can say we're stealing from the solar inverter industry, where they have topologies where they've kind of figured out how to get rid of the ripple on the electrolytic capacitors. And an LED, it's a solar panel is the model is a diode, and LED is like a diode. So you can kind of take those topologies and use the same different techniques, or you can do it in 2 stages, which is easier. And I'll show you maybe a couple of them. They don't break as easy. Vibrations, very good. They're beautiful. They're environmentally friendly in the sense that they don't have the mercury that some of the fluorescent lamps would have. Different colors, so they can be easily programmed now with the microchips. So you can do a lot with LEDs. You could say that according to the OIDA, that if you took one 60-watt light bulb and you replaced it with an equivalent LED light bulb, over the lifetime of the LED, you'd save 12 pounds of sulfur dioxide, 3,000 pounds of carbon dioxide, just one light bulb over the lifetime, no mercury emissions, 18,000 pounds of coal. And so the DOE is under this plan that they want to inject 50% of LED lighting, and they claim that in the United States that would eliminate the need for 40 power watt stations of the 1,000 megawatts. Okay, so there's a reason. One of the things about LEDs is that you are either converting to visible light or to heat. Okay? So one of the different benefits you could say about something like a fluorescent was that not all of it would go into heat. Okay, so you're computing, when you create light, you have other wavelengths that are useless, but they're not producing heat. So there's this heat issue with LEDs. That means that you have to separate your power electric drivers, and heat thermal management is a little bit more complicated. Okay. Oh, but in any case, let me read this to you. That I think we're seeing the LED lighting revolution. Can you read that? I wrote this cartoon, so I don't care if you are a cartoon. Anytime you have an idea, I want to see an LED coming from your head and not an incandescent. Okay, so LEDs are here to stay, and they do mean something, and it's not a fad. Flicker. So this is something that, what happened was, it was really 1995 that the white LED was invented. You took a blue LED, really, was invented around 95, in the early 90s. And then, once the blue LED was there, that was the missing link. Okay, so blue was a color that was very difficult to create. Then you could add yellow phosphor to the blue LED, and so it tricks your nonlinear eye. Your eye is a nonlinear filter, and it tricks it so that blue mixed with yellow and you see white. It would be a blue-white light. But you think about it, it wasn't until in the lab like 95 to 97 that happened. And by 2001, white LEDs were on the market. It's pretty quick. And to the point where we are now, 10 years later or so, that it's really a multi-billion-dollar industry. We're going to talk about flicker. Flicker is exactly what you think it is. It's a periodic modulation of the light. Now, you think that you have flicker, and if you see it, then you would say, okay, there's flicker, it's going on and off. You know voltage flicker because you're a power community, and we have definitions of voltage flicker, the IEEE 61,000, I think it is, or 610,000, right? But just because you don't visually perceive it doesn't mean that biologically there's not something going on in your head, okay? And so that's the difference between sensation, where your body is detecting it, and perception, you detect it, but you can say, okay, I see the flicker. I mean, what makes you think that as soon as you don't see the flicker, that there aren't neurons firing in the head, like the flicker is causing that, and that wouldn't have a biological effect? You can look at different types of light. This is just a 60-watt bulb, and we define flicker usually by what we call in the lighting industry percent flicker, which is the max minus the min over the max plus min, which is basically half the peak-to-peak flipper. So here we can see that you would have a percent flicker of 6%, which means peak-to-peak 12%. If it's symmetric, that's what it is. It's inherent of the lighting industry. But here's the magnetic ballast fluorescent tubes, and we can see that you would have usually it's about 20%, 20 to 30%, the old magnetic ballast. And then here's a CFL. And then we have here some LED lighting, and they can be of any form. Not only any form, but this is 120 hertz flicker. 120 hertz flicker now, we can see that this is pulse width modulated. Okay, so this is 100% flicker. This is something like, I don't know, 30% flicker, 40% flicker. And this, it's hard to define by that definition, but this would be a very high frequency flicker. Okay. And the thing about it is that high frequency, your body doesn't have as many biological effects. What we're worried about here is this 120 hertz flicker. So what happened in the history of lighting was that in the early 1990s, magnetic ballast and fluorescent lightings were there, and people started to complain about headaches. And they would say photosensitive. Some people would say that in the corner of their eye, if they moved them, they would actually see the flicker. Or if they do this, they could see the flicker, like a stroboscopic effect. Some people are more photosensitive than other people. And that problem went away right when the research was coming out to kind of explain some of the medical reasons that occurred. The reason it went away was not because people were concerned of the ethics, but because of the power electronics, high-frequency magnetic ballast. Right? So now you were switching at kilohertz. You would have better power efficiency. It was a cost, efficiency, and size reason why it went away. So the problem went away. All of a sudden, LEDs came. And the community just was not aware of this research. And we started to see different driving methods that brought the issue back. Okay? Now's the time to make a decision about how you design these power electronic drivers before it really becomes widespread, that the LED lighting. One of the things you got to be careful about is that it's a pervasive technology. you could say whatever is right. If I know that I don't like that lighting, that's fine. I won't buy that bulb. Okay, so maybe we just label the bulbs if you think it's fair. Suppose you are photosensitive and you go to a mall. You had no choice between that light that you're walking through the mall, and I've been called to malls where people had seizures. And I go with my flicker meter and I see it was a failing old magnetic ballast, because when magnetic ballast fails for fluorescent lighting, they actually would produce anywhere from 5 hertz to 50 hertz flicker. So it would just be varying, and that can put somebody into a seizure. So that's the problem with lighting, is it's pervasive. People don't have a choice when they walk in a building. So there's issues that we have to take care of. As a matter of fact, is anybody here photosensitive? Have you been diagnosed with seizures or anything? You would know. Okay. Now's the time, right? So, in fact, this is absolutely insane. I bought this on the market. It is a LED flashlight. So you shouldn't have an issue like this if it's a DC power source, because LEDs run off of DC. Why make it flicker, right? So what happens is under high brightness, it's here, and that's actually flickering. Now, some photosensitive people, if we turn the lights off, move their eyes around like this, back and forth, okay, that's called a saccade, they could notice it. Or they could do this, and they'd see, even see the stroboscopic effect. It's the flicker, okay? So you do it here, the lower brightness. In fact, I don't know why they do it, but they do it 57 hertz. Some people would be able to look at this and not move their eyes and see it. As a matter of fact, I say about half of you could, okay, if the lights were off here, okay? And this is crazy, because to turn it off, I have to do that, okay? Now, look at that, because none of you would know if you were photosensitive. Not one of you feels well if you stare at this. 100% of the room felt a little queasy. It's impossible otherwise, unless you're a Vulcan from another planet. All right? But to turn off the flashlight, you actually had to go to that unsafe mode. Okay? Well, that's something that we're trying to get rid of, right? So let's talk about eye saccades. Eye saccades are the motion from going from one eye to like view one here, and then quickly move your eyes to the other location. Now, that one thing we just talked about was flickering lights. Well, another way to get the light to appear at different parts of your retina is to move your eye, right? Same thing. And, well, I'll tell you what, when you're reading, you're moving your eye. So you have to be careful about the flicker. As a matter of fact, you can do some experiments. You look here, and we can do an experiment, and I'll show you what we did here, and we can flicker that at different speeds and tell people not just look at the light, but look at a dot to the left, a dot to the right, go through it and tell me if it flickers. Then we can change it and make it solid and do it again, and there's a double-blind study, so you really, say which one flickered, which one dot, and you get a very precise thing. And you would be surprised, I'll show you the results, about how high a flicker any normal person can see. Remember, now that's a fast eye saccade, but when you're reading, if you're a fast reader, you might be approaching about 1/10 that speed. So that's a worst case scenario, and we have to ask ourselves, what would do that? And you notice the flicker. I'll tell you, if you're noticing flicker all the time, you will not be able to concentrate. Your typing rate goes down substantially. You'll get headaches. It's just a known fact. Some of you may have noticed this at night. There's this myth that if you flicker these LEDs, you say, why do it? It's DC. It's a myth that it appears brighter. It appears brighter for like the indicator light LEDs. Above a very low luminance, once you flicker, it doesn't appear brighter. Okay? So in other words, what I was saying is the average, you say on average I might be at 10 lumens, but if I flicker at 20 lumens and then 0 lumens 50% of the time, then I think that appears lighter. It's false. It's like at 1 lumen that accrues. An indicator. That's true. So people understood that, and the car industry went ahead and some of these LED lights, and I find this very annoying, and I'm sure you've noticed this. A lot of these LED taillights, you'll move because you're moving like this, and you'll notice this, okay? That's the strobing of the taillights when your eyes are moving, or in fact, it's called the phantom array, okay? And this was named in 1987 by Hirschberger, and which is the idea is that you can flash a light, and you'll actually begin and move an eye saccade, and you'll actually see multiple, like a stroboscopic effect, okay? And we can do an experiment. Like I said, we can take a line, and we can flicker it, and just ask the participant which one do they see. And we can control the flicker rate. We can do it in a controlled room, worst case analysis, Okay, so it's dark and it's absolutely the worst case. So it's basically white light, or here it was, yeah, greenish, right, and a black surrounding, where reading would be black surrounding and white light. So it's the opposite. So we have to go to that next step. And so you can say, which do you see? And then you can kind of do an experiment like this. So it's not just a guess. They have to choose one or the other. Okay? And then if you get above, if you get it right 3/4 of the time, then you're doing, we say that's kind of a threshold. That's where the flickering rate is. So half the time if you guess, one flickering and one not, then that would be, anybody could guess half the time. But if you get it above 3/4. And the rule is that it's about 2 kilohertz. So in other words, if I flicker on and off a pulse width modulation, 2 kilohertz, which is much higher than most people think. Matter of fact, you might wonder, what is it that most people can see if I'm just looking at an LED light? And I would say that's around 60 hertz. Most people cannot see the flicker 90 hertz. And then a small percentage of people have claimed they can see it up to 110 hertz. Okay, but 50 to 70 hertz is where most people can notice the flicker. But that's when you're looking straight right at the bulb. In fact, one thing you don't realize is that when you think you're looking at a bulb, if your eye is not moving, you actually can't see anything. It's a big blur. Your eye is moving back and forth and vibrating so that the different neurons are exciting and the light is hitting different spots so that then you can notice the image. But here it's 2 kilohertz. And it's very similar to the stroboscopic effect. The stroboscopic effect would be shine a flickering light and move something. Okay? And you can do, people at RPI have done a study, and they said at what percent flicker, remember percent flicker is this a little bit different. It's kind of half the peak-to-peak ripple, max minus min over max plus min. At what percent flicker do you detect stroboscopic effects? And they came up with a formula. And I think the reason I presented this formula was so you could see at 120 hertz what it is, because we're about to go into the power electronics, and we see that that's where the issues are, at 120 hertz, because we have to use power factor correction circuits. And you'll usually have 120 hertz ripple. And what they discovered is that it's about 13.6% flicker, okay? Which was right about, well, certainly people could see that in the old magnetic ballast. So which means you can create an experiment. If you had these fluorescent tubes here and they were on magnetic ballast, you could create some experiment, maybe not general, and you could notice the stroboscopic effect. Yeah.
Detect here means that the observer could actually realize it's flickering.
Yeah.
So it could be much worse for a health reason.
Right. That's right. So that's a good point, because there's absolutely nothing that suggests that 20%, well, we know, well, let me show you. We know some studies where 20% to 30% flicker would cause headaches. So I guess that's lower than that, but let me go into that. So that's detect. Let's talk about, though, what the issue would be. I think the issue might be, okay, you detect it. First of all, is it annoying? So as a consumer, you might want to know that. But will it make some people not feel well or get tired? Okay. So first of all, the range from 3 to 70 hertz flicker is known to cause in about 1 in 20,000 people photosensitive epilepsy. Okay. But there's also this range of 120 hertz around that people have done studied on. And people who claim they don't feel well, they get tired. People have done typing studies, so they type and they type at a slower rate. So performance is lower. And then there's the famous studies by Wilkins in 1989, which was very carefully done, that they did a double mask study of headache and eye strain. So they compared conventional fluorescent tubes with magnetic ballast. This was in Europe, so it'll give you 100 hertz flicker. With, let's say, I think he was saying it was about a little under 25 to 30% flicker. And then they would put some offices with those magnetic ballasts. Then without them knowing, they'd come in at night and they would change the ballasts and try to keep the lighting at that time as identical as they could in terms of luminescence and quality of light. So, and then they would go back and do 20 kilohertz high frequency ballasts. Then they change them back and forth, and you do surveys. And some of the surveys were very interesting. One was they could measure the time that people kept the lights on. They found out that very noticeably that the high frequency lights were left on substantially longer, so there was a certain preference that was obvious. But that they really had, the big thing was 2 to 3 times more complaints of headaches if you use the 100, I put 120 hertz, my apologies, it was in Europe. The 100 hertz ballast, the old magnetic ballast, that the people complained about getting headaches over this period of 6 months, 2 or 3 times as much. So we can go ahead and we can kind of perform the different types of risk assessments that may occur. And I want to get into the power part of it very soon. But we can see that in the red area, this is a hazard matrix analysis, you have photosensitive epilepsy, red meaning very, very high risk level, and maybe migraines. So it could be very severe where people suffer from migraines and they may miss a week of work because of a bad migraine. Stroboscopic effect, it just depends on what you do for a living. If you notice this, in the lab, okay, maybe, but suppose you're working with rotating machinery, that can be quite confusing, and so in certain dangerous machinery, you want to make sure you don't have the stroboscopic effect. So it's quite there. But then here, depends on who you ask, a little headache, should you worry about or not? And then there's some research about that autistic people are aggravated tremendously by the flicker. Okay. So what makes the LED drivers different, and why is there a concern specifically about LED drivers? The basic mechanism, just to remind you, is that an LED is a diode, and diodes run off of DC. Okay? A couple things here, and I apologize for not really presenting much control, but I do want to, I guess I can mention some controls in honor of Professor Bensman here, to say what some of the control issues are. First of all, when you buy an LED, you just don't know, this is the IV curve, you don't know which LED you're going to get. So that for the same current, you might have a different voltage. Okay, so there's a voltage variation on the LED, right? So there's parametric uncertainty in the model. You can pay a substantial premium, and they'll test it for you, and they call that binning. And then the more precise binning that you need, you say, well, within 10% I need this voltage level, and you pay a little bit more, okay? And it doesn't matter even if it comes from the same wafer. That's the variation that you're going to get. The other thing is temperature variation in a diode is going to make it change. So if we want to precisely control the current through an LED, then we have this wide variation, and that's where some of the control algorithms come in to make sure that despite the variations in the LED, you adapt your controller to it. Okay? But we see we do need a DC current through the LED. Okay? So if it's DC, there should be no flicker. Okay? One thing, though, is that if we have DC current through the LED, we have that the current is basically proportional to the intensity of the light. So by controlling the current, we are actually controlling the perceived brightness of the LED. So we're going to do power converters that do control of the output current versus the voltage. So that's a big concept. We're going to put a source here and make it be like a current source. Okay? And so that's the big concept, that brightness is the perception of luminous intensity is proportional to the current that's through that LED. Okay. So what's the issue, the concern? Really, it's AC. Despite this one flashlight, which made no sense why you'd want to flicker it, it's the AC LED, and it's how you drive your LEDs. You have to go AC to DC somehow. And to do that, there's various ways to do it. One is to put an AC to DC converter in, and we know that they usually will have the twice the line frequency harmonics anytime you go AC to DC. Okay? And the quality of the harmonics often depends on which driver you're using and the cost of parts. This was one of the most frustrating things for me when I was with this company called Exclara, was we developed a lot of digital technologies that we claim we were the first to be able to work off of a residential dimmer switch. We have one of the first patents that did that, because that was, I'll show you some slides, that was a big problem. Now a lot of companies do it. But at the time we were one of the first. And one of the things that kind of is so frustrating to me is that the consumer, the people like Philips, all they care about right now for this is cost. So it's a commodity. So we would say, but we can go dimming. And they say, who cares? It's a $10 bulb. We want to buy it for all the power electronics and parts for 50 cents. That's what they'd say. We could sell it to them for $1, which means we'd make a few cents on it, it's a commodity, so you have to sell millions. They say, who cares? Get rid of the features. Let's just go to, get it down to 50 cents. We need to bring the cost down. So I don't know, there are a lot of entrepreneurs here. That was quite frustrating for a thinker to try to get into something like that because it's just a commodity. It's not something where we could put a lot of our good ideas in. But another interesting technology, though, is that you don't really need, the cheapest way to do it is without the power factor correction circuit in the front. Because what you can do conceptually is just put your AC source through a full bridge rectifier. And you're going to get a voltage that looks like this. Okay? Well, you're also going to get a current that looks like this too. All right? So what you've done is you've basically got 100% flicker, okay, at 120 hertz. All right? So all of a sudden you ask, why is all this discussion going now about flicker? It's because of this technology, really. 100% flicker at 120 hertz, and we're back to the old magnetic ballasts, which we thought we had gotten away from in 1990, but it's even different because it's 100% flicker. It's no longer 30% flicker. All right? So one would expect that any of the attributes, your biological effects, would increase because of the 100% flicker. Okay? The other thing is you can get rid of this full bridge rectifier. This is called the AC LED. Now I'm showing you the most simplistic ones when they first came out. There are a lot of variations on this called AC LED stacking, which Xclair, my company, has done. And so what we have is the positive current goes through this side and it might produce this cycle. The negative current would go through this side and produce that cycle there. So we eliminate the bridge rectifier. The net result, though, of course, is the same output here, 120 hertz flicker. Okay? These are on the market. What happens, though, anytime if you have a full bridge rectifier and you lose one leg of the bridge, of course, you're going to get 60 hertz flicker now. But the difference is that this is now, in either of these, if you lose one of these legs, is at 60 hertz at 100% flicker. And that's actually at a point that a lot of people would, a measurable percentage of the population, small percentage, will go into seizure. Okay? So we would recommend then, of course, that if you have to have some sort of alarm. I mean, it's not very hard to put an alarm on your chip to say shut off if you're in this situation. Right? So at the time when we started this standards committee, nobody put an alarm on. I would hope now that they do. Alarm, not a physical alarm, the power alarm that says shut off. You're flickering at the wrong rate. But what about power electronic drivers? Okay. Well, Energy Star would regulate that if you would need 70% power factor in residential and 90% power factor in commercial applications. So you're going to need a power factor correction circuit. You either normally would choose, this is not exactly true, but it was simplistic, single stage or two stage. Or you have these other techniques which are very popular, which borrow from really the solar industry of sort of like combining topologies and canceling out flicker, but they're adding extra parts. I've actually got a couple of circuits there that do some of that. But we talk about single stage LED drivers. This is just a flyback converter. And so you rectify, and this is just to power the control circuit. This goes to a flyback here, and this is the housekeeping also to power there. And so what you'll see is that if you run this in power factor correction mode, a lot of you know this. You've had power electronics, but you might need power electronics too. You might run it in discontinuous operation mode. It's one of the easy ways to make sure that you have good power factor correction. It could also be done in continuous conduction mode, and you'd have multiple feedback loops going, so feed forward and feed back. And you get signals that would look like this for a single stage power factor correction. In the sense I've taken this from a scope and I've put it out of stage so you could see that they're not necessarily on top of each other. So one is voltage and one is current. So there's a little bit of a phase lag here. Okay, so that's pretty good power factor correction. It's not great, right? But we could put that a little bit closer. Over here, though, what we have is the AC input current, looks very clean. And this is just the ripple, not the DC part of the output current. And what we can see though is that this is 200 milliamps per division, as is typical for single stage power amplitude, power factor correction. This would be about, let's say, 200 milliamps, and it was a 500. It was a little bit less than half an amp through the DC through the LED. So 400 milliamp. You're looking at about 40 to 50% flicker, but some would be 100% flicker by my definition of half peak to peak. Okay, so what happens then is single stage, you're going to get this 120 hertz flicker. All right, so you're power electronic engineers. Now you're aware of the issue. Question is what you do about it. You might do 2 stages. Now the thing about the 2 stages is that you can get a very nice waveform and reduce the flicker. This percent flicker is about 4%. Okay, and there's a lot of, I didn't go through all the topologies. I have some others too, but there are other topologies. It doesn't necessarily have to be 2 stage. A lot of things you could put like through a single stage flyback. You can put another winding on here and put it, and so send energy to one side and then send it back bidirectional. So you're canceling out the flicker back and forth, like sort of like the Illinois approach to, I think I've seen for some of the solar energy circuits, the inverters. It's very similar. You grab energy when too much energy, you take the energy out of the flicker, and then when it's at the lull, you send it back. Capacitive valley fill sometimes you can use too. But in any case, 2 stage, you can also do this. All right. But this is the design consideration. We're trying to sell parts to a company, and we're at about $1, and they're saying, well, can you make it 50 cents? So they don't care about this. They say, all right, give us single stage then. All right? How cheap can you make it? Well, this is where the community is right now. I can say, though, that it's not so hard to figure out. You can eliminate flicker completely. That is, suppose this was the AC to DC converter, and you got something and it had that small amount of flicker there. So now here. It's not that hard for us to eliminate all that flicker because we can put, even in multiple branches, a linear regulator on each one, right? And you just clamp it and take the power out and make the flicker 0. So I think the message here, though, that I would like to say is this is not a technology problem. We have solutions. If you say, what is the flicker that you want? You can find a topology that will give it to you. It's a matter of, instead, flicker versus cost versus performance, right? So I started off the talk and I said, very few technologies have we got where now an engineer coming from a power lab actually has to make these choices about how they feel about the research and what the certainty is about maybe biological effects. You don't even have to think about that usually. But in the LED lighting industry, people are becoming aware and now fighting over whether, well, people say it's an issue, but how much of an issue is for the power electronic engineers and the lighting community to design. I'll tell you straight out that there are big arguments going on, because if you have a product that is this, then if we say that flicker is bad, and Energy Star comes out and says we don't want these on the market, what happens to your product? What happens to the jobs? Right? Which is worse, causing a few headaches or laying off 1,000 people? All right. Anyway, this is not for me to determine, but it's to bring, as an engineer, to the forefront of the community and to the government topics like that. And this is what actually, let me just look at this. Yeah. What actually sort of started it often was the phase modulated dimmers. You know those dimmer switches on the wall? This is really what is caused people to go into seizures a couple times. A lot of the initial LED lighting power electronic drivers simply failed. And this was the original work that we published. There are a lot of ways to do it. One of the things that's very strange about it is that dimmer switches, they actually need a certain power bulb to be on the market in order to operate. Okay? If you don't have enough power in the load, then the dimmer switch starts to trigger spontaneously. The latching currents and the holding currents don't exist. Right? One of the benefits, though, of an LED bulb, 2 benefits. One is that you should be able to dim them very easy. Okay? You can either pulse width modulate it, and control the average value, or you can lower the current in it. Okay, so that's a great advantage. Great. We don't have the problem of fluorescent bulbs. But the other advantage is that they are really, really low power, right? Take a 60-watt bulb, in a few years it's going to be 5 watts. Guess what? Your dimmer switch won't work on that, all right? And it will fail. The trick that people have to do is either add more bulbs, well, there are a few tricks, or you actually have to add a resistor. So the benefit is, you know, they're great efficiency, but if you work them on a dimmer switch, we're going to put another active, basically current sink in there, and if it's on dimmer switch, we're going to just still always draw 10 watts, right? We have to add loss to it to make it work, okay? Some actually fail, and they fail in a very dangerous way, and solutions came out, and we were one of the people to come up with one of the first solutions about how you make them work on dimmer switches. This is actually one that failed, one of the first ones on the market that failed. And so we just hooked the dimmer switch on it. And I don't know if you can tell, this is 3 hertz. So we try to dim the LED bulb we bought on the market, and it would flicker at 3 hertz. Everybody would notice 3 hertz. That, though, would be very, very dangerous for people who are photosensitive epileptic. Okay? So you have to be real careful. What are some of the solutions? One is that you actually have to add, you have to add a resistor and a sink on it, and make sure that you're always drawing current, even when the dimmer switch wants to fail. And the other is the so-called capacitor valley, the holdup here. See, a dimmer switch, I don't know if you know how these dimmer switches work. I'm sorry for going back and forth on this, but you've got this problem here that a dimmer switch basically chops the signal of the power. Now, through an incandescent bulb, that just means that it lights at a dimmer level, right? So you're putting in a chopped signal. But when you chop the power here with a power electronic driver, what people didn't realize was you're getting off a dimmer switch, it's chopped, there's no power to your circuit anymore. So your power to your chip failed. So they would just shut off. So people came up with a solution of power on, power off, which means that when the dimmer was off and chopped, we'll shut down all our power electronic circuit, and when the dimmer turned back on, we'll turn our power electronic circuit back on, our AC-DC converter on, because those have a 100 millisecond response time, much quicker than the eye can see. Okay, and then we'd run it on there. But that would be a 120 hertz flicker, and people said, no, don't do that, because we can actually notice that while we're even writing, you know, the stroboscopic effect people did. So they put this capacitor, you've probably seen this in many different circuits, capacitor valley fill, so that even when the circuit is off, you've got these capacitors here. They happen to be electrolytic, which don't last as long as the LED bulbs. So these might have a lifetime, you know, if you designed them precisely of 5 years, but then you have to over-design them to make them last to 20 years, you know, 25,000 hours. So you have a lot more capacitors there. And they would hold up the power to your chip so that if you're dim, then this is off, and there's no power there. You're sensed that there's no power there. It's a blanking time. And then you now can pulse width modulate this and dim it accordingly. Okay? So the idea of dimming was that you can modulate the common ways to modulate the time that this is on, and you've controlled the average value. Okay? So you're using a signal here, the signal here of blanking time, no power coming in from the dimmer switch, to convert that to a pulse width modulated gate signal here. When it's open, no power goes through the LED. Okay? But look at this. We got a nice basically power resistor we can always have to make sure that we're working on a dimmer switch. We can add power loss so our dimmer switch works. It's kind of backwards. Why to go to LED lighting when we're just going to add a resistor to it? Right? And different outputs of lighting. We can see that we have dimmer switches, and some actually dim at, usually they're at 120 hertz. So here's some test signals. This is on a switch. This is at a dimmer switch for an LED bulb, typical LED bulb, 75% dimmer, 50%, 25%. And then down here, this is a bad bulb, 0% dimmers. This is what I find so annoying. I guess I find so annoying because I put the dimmer switch on 0. If you have all these other bulbs on, and you're still getting about, you can tell you're getting 25% power. That's only because they're doing it cheap. We know how to do it. There are a lot of patents out there who can bring this down to typical of a bulb, down very low to 5% dimming. But they don't do it because of the cost. Okay? So that's where the technology is nowadays. All right. So with that, we step back and just simply say that it's very rare that power electronic designers have to actually think about what the impact of their technology is to the well-being of society. By society meaning you have a choice when you design the driver about how much biological effect you want to the lighting in that bulb. And this is a debate that companies are having right now about what is acceptable and what is not. Just as an afternote that I do work on this committee, and we're about to come up with recommended practices that we now know the answer from this research. We know safe. It's very tough for me to carefully word this without the lawyers helping me. But we certainly have regions where we know if you operate the flicker in these regions, for each frequency we can tell you a region of flicker that it would have minimal biological effects. That does not mean that if you're outside that region that it's unsafe. But we at least have a starting point to say they're very reasonable reasons. If you're not doing the AC LED, all it is the right capacitor and the right frequency. Okay, so we have those, but they're not necessarily, they could be conservative. So that's where we are now. And that's the purpose. So that's all I had, and I appreciate it. And I would like to say, hold on, that with this, probably it's 25 years too late for me to say that thank you, Mr. Bensman, for my advisor here, Professor Krein, for all that you've done for my career. And I've come back here. It's changed completely, but I owe so much to University of Illinois. 25 years too late, but with great. Yeah, I look the same, a beautiful liar. Thank you. Thank you.
So when you're talking about, kind of not common, but you have different priorities and people, the companies making it, like they want to really reduce costs. I feel like we're running into that with the PV industry as well. What kind of, how are you to overcome that, or what strategies do you have to kind of push the technology forward? General question.
Yeah, it's a great question, and this is. So I can only speak from experience, and in my opinion, my experience is not terribly successful. But we got in on the LED market too early. And I think that was problem number one for me. That what we saw, I thought I could see it. We're graduate students and we know the field. So I saw the technology of the white LED, and in 1999, we were trying to figure out how to make a company from it. Well before, we said, we got to jump in before it happens. In 2001, we thought we had all the money lined up, and around there we had a little bit of money, and we would have been one of the first companies in, and then 9/11 came. So we lost some of it, but we were there. And so we created this patent, and it was too early in the sense that there was no market for it, and we couldn't get the market, and so before we knew it, National Semiconductor, TI, and all these things could jump in, and it was very tough. And as soon as those companies came in, it was a commodity, okay? And then what we tried to do was go with features, okay? And so I wish I could tell you the success, but so we have these patents, and these patents really are the ones that allow you to work on with a dimmer switch. So that's our technology. But the patent field. A few years later, everybody else says they've got a patent on this, and it costs $1 million to sue, right? And then you end up trading the patents instead of suing. So that strategy didn't work as well either. And then what we had to do was we had to give in, all right? Forget the digital power electronics that we did. Forget the great dimming. We could go down to 1% dimming level. We said the money is in the system. So if I had to say that, is the money is in the system and not just in the power electronic driver. So we went and they were saying, we want a 50-cent power electronic driver, and baby, we could sell for $1.10. It was terrible. So we said, forget it. Let's build the whole LED lighting lamp and sell it to overhead street lighting. And that's how we got our revenue. So I would say system. It was a long-winded, but that's very painful. And I got so frustrated, I would say I was the only one in my company of the co-founders that made money. And the reason was I got so frustrated, I jumped ship first and said to the venture capitalists, buy me out. And 2 years later, the venture capitalists, I can say it now, I'm allowed to say it. They said they took their first, they didn't do well on their other investments. It drove me crazy. We were bringing in some revenue. And so let's say we were bringing in 1.2 million a year. Not great in revenue. And they put in 10 million. So it's really like an 8 to 9 to 1. Not bad for a startup venturist. And they came in and they took their first offer that was break even, which was they put in about 10 or 11 million dollars. They put in their first offer, which meant that all the other people didn't make any money. They just took break even. Why would you do that? By the way, 10 to 1 on a new company, revenues to expenditures, is pretty good. And we were showing nice projected. But what happened with the venture capitalists was that they, their other investments were doing bad. And so they said, well, we're going to break even, and they have different priorities, and so we're going to make you sell. And so I was the only one that actually made some money because I sold my share when it stopped becoming fun. We had digital technology that could do all this dimming, and we ended up basically doing analog drivers because we had to do revenue. Okay, so system was the only thing, and stay away from venture capitalists. Sorry. Robert?
Could you comment on what international standards? I think Japan is a little bit ahead on the whole flicker. The U.S. sort of follows IEEE standards, if you will.
So right now, everybody is relying on whatever we put in our report, which is not published. So there are no standards on the flicker. Every international agency is waiting for us to release the report, which we hope to come out this year. I would say the way it's going to work in the United States is there's going to be this huge debate, and who knows what happens. I would expect in China that they're just either going to say yes or no. The government, we're in contact with them all the time. And if they say yes, then they're going to go be the first country to go to a safe flicker, or they're going to say no, because they can mandate it. So, and Europe is also, we're in touch, but they're relying on this report now. So there's nothing on the flicker right now. But I mean, just to go back to it, you know, different lighting. Would you feel safe, even if, say, so it's not certain, would you feel safe if in the hospital they used the AC LEDs with 120 hertz flicker? Or kindergarten classrooms? Kindergartners are particularly susceptible to flicker. Well, you know, I feel a lot less safe about that. I'm more cautious about that than I would in my home. Because I can't even see flicker. 50 hertz, I'm very, very intolerant of it. So, were there more questions? Yes?
What percentage of LED products in the market have like sub-optimal flicker properties now?
Well, I'm not allowed to tell you what suboptimal flicker is, okay? We understand that.
What fraction of the market do you think is AC LED?
AC LEDs maybe 10%, very low, maybe 5%, okay? So it has not done a big market. But a lot of the flicker is in two-stage power factor correction because they just, if we told them what a safe number is, they would go it, okay? And they're just waiting for us to say what the safe number is. Yeah. Yes?
So would it be regulated or integrated into like Energy Star?
Right. So it depends on the country. Energy Star has announced that to get a certification, they're waiting for our report. You know, at some time, you might get a sticker on it. But what would they do? Energy Star, doesn't matter if you get rated or not. You can still put it on the market. So it's an encouragement. The other thing is they might have different levels. Or in the video game industry, they simply have a warning in the manual that says, if you're photosensitive, please don't use this video game, you know, and you know it, okay? It's a little different now because, like I said, people are walking in to a mall and they might not know it, that it has a certain technology. I think the first thing, though, is you got to make the community aware of it and then let them decide, sort of. But if I had to guess, it'll be a warning label of some kind, or to get a certification. From Energy Star, you'll have to satisfy some flicker requirement.
Well, thanks again.
Thank you.
Perfect timing.
All right.
So I'll,
Oh, thanks.
I'll cover less than something with it. So
I'll call you tonight.
Tonight.
Yeah, I'll call you tonight. And then we'll, I'll tell you what my